Hello, and thank you for joining me today in SBC 201. This is an online walkthrough for the Generic Processes 3 lab. This is the lab following Generic Processes 2, which, if you will recall, focused on exponential growth models. Today, in Generic Processes 3, we'll be practicing the examples that model an exponential decay function. Exponential decay is basically the inverse to a function of exponential growth. So it's important to go through some of the vocabulary we picked up in Generic Processes 2, as it will relate to what we see later in today's lab. Now, if you go over to part 1 of Generic Processes 3, Exponential Decay Models, it will ask you a few questions to refresh your memory to what a reinforcing loop is, what kind of an effect a reinforcing loop can have on the stock and flow, and why a model may be identified as a reinforcing loop. There's also a question that will remind you how we were able to find the doubling time of a model in Generic Processes 2. This will be important as we'll use a similar function to account for exponential decay later in today's lab. So go ahead and answer these questions for yourself. You may want to refer back to Generic Processes 2 to refresh your memory, or please email your professor or TA if you are confused by these topics that part 1 brings up. For number 4 in part 1, it will ask you to show how a causal loop would be written up with this example. So go ahead and work through that as well. Again, if you have any questions, please do report back to either your TA or your professor so that they may explain these concepts to you if you do not understand them. However, if you completed Generic Processes 2, you should have a general understanding of how those concepts work. So moving on to part 2, we also have another causal loop to show the influence of a deer population if deaths were to go up or down. So based on the information you provided for part 1, you'll be able to determine if this is in fact a reinforcing loop and what will happen as the population of deer go up, what will happen to the deaths, and also as the number of deaths goes up, how that will impact the population. So next, when we move on to part 6, we're being asked to prepare a deer population model. So assume there are no births in this scenario. We're going to start with an initial deer population of 100 and a death fraction of 0.3. So let's go ahead and get that started. So we're going to go ahead and take our stock here and label this deer population. Next, we will take a flow, and we're going to draw an outflow coming out of the stock. Label that deaths. Let's go ahead and back to our lab and see what they're asking for. So assume there are no births in this scenario. That would mean that we have no inflow for this model. And we're going to start with an initial deer population of 100 and a death fraction of 0.3. So let's go ahead and start with an initial deer population of 100. For units, we can enter deer. And for the outflow of deaths, we do have a death fraction, so we'll go ahead and put a converter there, label that death fraction, and enter its value of 0.3. For the units, we can go ahead and label that deer as well. Now we're going to take as a connector and connect the death fraction to the deaths flow, and we're also going to connect the stock of the deer population to the deaths. And now when we click on deaths, we'll show how these two interact with one another. So the outflow will be determined by the deer population multiplied by the death fraction to give us the amount of deer per months that will be flowing out of the stock. So looking at number 6a, it says to consider a model for a deer population with a deaths outflow. Assume there are no births in this scenario, and start with an initial deer population of 100 and a death fraction of 0.3. This deer population model is also exponential because the more deer there are, the more deaths there are, since deaths are a fraction of the current deer population. So what they would like you to do here is draw a sketch of your model in the space to the right. Use the same diagram patterns as you did for exponential growth, except use an outflow instead of an inflow. Be sure to label each icon correctly and place the appropriate value in each icon. So once you complete that, you move on to number 6b, and it's asking you to consider the behavior pattern for the deer population over time. Will it increase or decrease? And as it states, this should be a rather easy decision as we are dealing with deaths. Will the graph of the deer population be a straight line or a curve? This may take a bit more thought. Just do keep in mind that if we had exponential growth or exponential decay, that would contribute to the shape of the line. So that's just a little hint there. Should be a pretty straightforward question though. And then finally we're going to move to 6c, and it asks us to create the model. Set up both the graph and the table showing the deer population. We're going to leave dt as the default value and run it for 20 years. So let's go ahead and put this. Okay, so 6c is saying to create the model. Here you can see I have the stock with 100 deer as my units. I have the death outflow, which will be the number of deer flowing out of the stock each year. And then we have the death fraction that they said was 0.3. Now, I'm just going to go into our run specs quickly, and it's said to leave the dt at 0.25, which 1/4 would be 0.25. It says to run it for 20 years, so we're going to go ahead and change that runtime to 20 years. The intervals, or time units, should be years. And then checking everything else, that everything else is correct. We can go ahead and run this now and see what type of an outcome we're going to have. The question asks for a table with this information, so let's go ahead and drop a table here. In that table, we're going to include the deer population, so we want to see how it changes over the 20-year time frame. And then we're also going to add a graph to see what happens graphically to this function. And let's go ahead down here and click run. And as you can see, if you predicted in questions 6a or b, we have a downward sloping curve. It is not a straight line, but it is a curved line. As I mentioned, it was an exponential decay, so this would happen at a very fast rate initially and slowly level out to 0. Never ultimately reaching 0, but it's the way exponential functions work. And as you can see here in the table, we can see that we drop fairly significantly. And as we go lower and lower, the amount of deaths seem to taper off. So you can go ahead and answer question 60. It says, does this graph show the runaway behavior of the exponential growth model? Now do be sure to check that your graph looks like mine after you run it. If for some reason your graph does not look like mine, it's an important note to backtrack and be sure that all of your input values are correct. Again, you want to have 100 units is deer, 100 deer in the deer population. The death fraction should be 0.3, and the flow will be the deer population multiplied by the death fraction. Once this is correct, we can move on to number 7. And it's asking us to think about the pattern of behavior for the deer population if the initial number of deer in the population was changed to 100, from 100 to 200. What do you think will be the same about the population pattern over time? And how would you recognize this pattern in the graph? So you can go ahead and give that some thought and give your answer in the box. Then it asks, what do you think will be different about the population pattern over time? And how would we recognize this change or pattern in the graph? So with this, they're really asking you to give some critical thinking to what will happen if the initial value of the deer population is changed. How will the graph or model remain the same in aspects, and what would be different about those aspects? So next, moving on to number 8, you can do a sensitivity analysis to find out how the behavior of the deer population changes for a variety of initial population values. So right now we're going to go ahead and learn how to do that sensitivity analysis. So we're going to use SensiSpecs to set up a sensitivity analysis and to do 5 incremental runs for initial populations from 50 to 250 deer. So before we jump into number 8, it is asking us to duplicate what we have already here. We're going to be changing a lot of this information, so it's important to save what we've done so far. So first, hit save in your file. You want to save this so that way you keep what you've done so far, just in case if the model happens to crash, your computer happens to die. It's just an important thing to keep it saved and on file so we can always revert back to it if you have to stop. Secondly, you want to minimize our graph and table and bring them next to each other. And then we're going to take everything here, move it up into the top right corner. So just so I have more space on my page. And then we're going to sector this first portion as our answer to the first question 6. Doing this so that way when we submit the overall lab, it's sectioned off for the professor, and so that they have evidence to see that you did the question and how you did the question and what your results for the question were. So we're going to lock this sector, but before we do that, we're going to go into the table and click Preserve Table Data. This is just so that way any future runs that we do will not impact this table. We can also do the same thing for the graph. We're going to preserve the graph data, so that way anything we do run after this will not have an impact on what we have within this sector. And then finally, we're going to lock the sector. Actually, before we lock the sector, let's name this Problem 6. There we go, so we know what this is referring to. Then we're going to copy the current. So then we're going to copy the model we have now and paste it below. There we go. So we're doing this so that way any changes we make to the second model, we can make changes to the second model without affecting what we did with the first one. So here, as you can see, once you copy it, it's labeled now deer population 1, So you know this is, actually we can change that to deer population 2, but you know it's the second model that you have with this information. So for number 8, we can go ahead and sector this off as well. Take the whole thing, move it up. Sorry, I'm very tedious about how this is all lined up. Yours doesn't have to be exactly this orderly, but for me, it just helps me to see everything a bit more clearly and understand what I'm doing. So we're going to label this problems number 8. And in problem 8, as I mentioned, we're going to be doing the sensitivity analysis. So first and foremost, let's go ahead and lock the problem 6 graph, so that way we don't affect anything in this sector when we run the results for the sensitivity graph. So number 8 says we're going to use SensiSpecs to set up a sensitivity analysis to do 5 incremental runs for initial populations from 50 to 250 deer. So let's go ahead and click on deer population. It's very, very important to do your documentation for each point in your model, so that way if ever you need to refer back to it, or a professor or someone else is referring to your information, they can see where your thoughts were at, or what you were aiming to complete with each model. So for deer population, we're going to say this is the stock, this is the stock for the population of deer with an initial value of 100. Now, I know this seems very straightforward and kind of obvious as we're working through the lab, but trust me, it does make things a lot less complicated when going back to it later, or when you have a much more in detail model. To have little descriptions of what each point is will help you and anyone else who's looking at your model. So for deaths, this is an outflow of deaths from the stock of deer calculated by the death fraction and the deer population. And finally, this is the death fraction for deer at a value of 0.3. And now, had I done this before I copied my model and made the second one, this information would have copied over with it. But since I didn't do that, I'm just going to go ahead and copy this information, paste it down for this as well. Do that for all 3 points. Boom. And now, because we're going to be making changes for the problem 8 sector, this is the stock for the population of deer with an initial value of 100. That's not necessarily true anymore. So we're going to say this is the stock for the population with varying values from 50 to 250 through a sensitivity analysis. So now we have a little better description of what is happening with this stock. So now we're going to open a table and a graph for this. Because we're doing a sensitivity analysis, we want to make sure that we turn on comparative for both the table and the graph. We're going to add deer population 2 to this table. I'll minimize that. Then we're going to do the same thing for the graph. Be sure that you mark comparative because we're doing a sensitivity analysis. If you do not mark comparative, you will only see a single run for one of your values. You will not see all 5 values or however many values you input into your sensitivity analysis. And then for this graph, we would like to see deer population 2. We are going to do run specs. So now for problem 8, we're going to run a sensitivity analysis with the deer population being our item of variation. The initial value will change from a range of 50 to 250 by increments of 50. Our initial value will change 5 times by increments of 50, with values starting at 50 all the way up to 250. So let's go ahead and make sure our graph and table are set to comparative, so that way the sensitivity analysis can be read on the graphs. If your graph and table are not set to comparative, it will only show one run of the initial value listed in the population, which would be 100. So now we're going to go into model settings. If you can't seem to get here, you can go into model and go to run specs, and that should bring up your model settings. Now, if you look on the bottom, on the 3rd tab, we see the sensitivity analysis setup. So we're going to go ahead and open that. We will have 5 runs, as the lab mentioned. Give me one moment. So the lab says we're going to use SensiSpecs to set up a sensitivity analysis to do 5 incremental runs for initial populations from 50 to 250. So we have 5 runs. What we're going to be looking at is deer population 2 as the variable. And then we have it set to incremental. We want our starting value to be 50 and our ending value to be 250. Again, the lab says to be sure that both the graph and the table are set to comparative, and both are set to comparative, so we should be good. Double checking that the sensitivity analysis is on for 5 runs in incremental values starting at 50, ending at 250. Now after that, right now I have it set so that any runs we do will only run for sector 8, or problem 8. So it's nice, again, to sector, not only to keep track of what you've done so far, but you can prevent any runs from occurring within this sector. Now, because we locked everything in this sector, it won't have an effect on it even if this box was checked off, but it's just a safe measure, so that way you're not complicating any of the previous data you've already found. So once we find the sensitivity analysis, we will lock everything here as well, so that way any future runs we do won't have any impact on that data we retrieve. So now we checked to make sure that the sensitivity analysis is in place with 5 runs, starting from 50 to 250. We checked and made sure that the graph and the table are both set to comparative, and now all that's left to do is to run the sensitivity. So we go to model and click run sensitivity, and the srun should have gone through. And so long as my computer will allow. Oh. And my model is not responding. So here's a prime example, folks, of why you want to save your models as you move along, because situations like this do happen where the program will not respond and you will lose any unsaved data that you have inputted. So unfortunately for me, I didn't heed my own advice, and I'll have to close the program and start over again. But luckily, I didn't get too far into what we did, so I should be able to get us back to that point relatively quickly. Just bear with me for a moment. Beautiful. So the new Stella Pro has a crash recovery, which is nice. So everything I did was not lost for all eternity. But okay, so let's go back and open up the graphs that we had. We have the graph and the table. And go ahead and put those side by side, and double checking once more that all of our information is correct in the sensitivity analysis. That both graphs are set to comparative and the table is set to comparative. Now we can go to model and run our sensitivity. And as you can see, we have our 5 runs here. 1, 2, 3, 4, 5 runs, all varying from an initial population value of 50, 100, 150, 200, and 250. And based on what we assumed in number 7 to happen, you can now see if you were correct in your assumptions to say what would be similar about the graph and what would be different from the graph compared to the graph we found in table 1. So because my system crashed, that information is not there, so I will run what happened in problem 6 very quickly, just so we have that view. You can see there in the table as well. And again, now you can answer question 7, or see if your answer to question 7 was correct in what were the same between the graphs and what may be different between the graphs.
So moving on to question 9, it's asking us to investigate the changes in the behavior of the system for a variety of depth fraction values. So what I did here was I copied once again the model, and I was sure to lock all of my previous information. So I'm going to go ahead and double check that the graph and the table are preserved, so that way any runs we run in the future will not affect the outcome of the previous runs. So because it's not showing up, I'm going to just run it one more time before I do lock it, so that we have that information. And once we do, we're going to preserve that table data as well as the graph data. And now that that's preserved, make sure that the sector is locked, and we're going to go ahead and create a new sector for question 9. Question 9. Alright, so the lab is telling us to return the initial deer population back to 100, so let's go ahead and check that that is still at 100. It would have been changed to 200 had you followed the steps from the previous question, so that's why it's asking you to change it back to 100. And then we're going to go ahead and change the Sensi specs of the depth fraction from 0.1 to 0.5 in steps of 0.1. So let's go ahead and take a look at our sensitivity analysis. That again is the third tab on the bottom. And as you can see here, we already have the parameters set for the depth fraction. It's going to increase incrementally for 5 runs. With a starting value of 0.1 and an ending value of 0.5. So now we should be good to go ahead and run the next sensitivity graph to see what the depth fraction will, how the depth fraction will impact the deer population. I'm going to run that sensitivity. So before we run the sensitivity, we want to make sure that the graph is going to show us still the geopopulation outcome. It will still have an impact. The death fractions will still have an impact on the geopopulation, since that's what we're looking at. So we're going to check in both the table and the graph that they are set to show us information for geopopulation 2. And be sure to make both the table and the graph comparative, so that way you are able to see the effects of the sensitivity analysis. Here we go. I'm going to make these a little bit bigger so they're easier to see. You can see the effect that the variation of the death population will have on both the graph and the table on the geopopulation. And if we just look at the graph outcomes before we go back to the lab questions, you can see that with an initial value of 100, as the death fraction varies, the amount of deaths will increase substantially per varying death fraction. As you can see here, it's relatively slower for a 0.1 death fraction compared to a 0.2, 3, 4, or 0.5 death fraction. The deaths will occur much more quickly and ultimately results in approaching 0. Let's go ahead and see what the lab has to say. It's asking how these 5 curves are similar. So I did just describe one similarity, being that the initial value was the same. You can go ahead and identify a few more similarities amongst the graph, and also the differences. I did note some of those, so you can go ahead and note some other differences you may notice. And then using this sensitivity analysis, we're going to complete the following table. Once again, we're asked what the halving time would be and what the quartering time would be. So we're going to go ahead and take a look at the table to see at what points the population would be cut in half. And again, it's an approximation. If you would like to use the graph to do this instead, as I pointed out before, you can click your mouse and drag and see roughly when the time will be that the geopopulation is cut in half. So for the section labeled Run 2 on the bottom, we're going to see that right about here, between 6.75 and 7, we are reaching 50 for our population, which would be the halving time. And if we look at the line labeled Run 3, we can do the same. And see that at about 3.5 to 3.75, we are approaching, 3.5 to 3.25, we are approaching 50. That was for 0.2. And then so on and so forth. You want to check the values of where the population is cut in half and fill in those values on your lab. And then you can go ahead and do the same thing for the quartering times. For the next section of the graph, it's asking you to calculate 1 over the given death fraction. So if you put 1 over 0.1, you will get a value of 10. If you do 1 over 0.2, you get a value of 5, and so on and so forth. You can calculate these values. Next, you're going to go into the next column of the graph, of the table, rather, and multiply that value that you got from 1 over the death fraction by 0.693. Now, keep in mind that 0.693 is a very significant number. You will learn that by the end of the lab. But by multiplying 1 over the death fraction by 0.693, you will get an approximation, or more. You will get a specific value, which is actually the halving time that you will see the death fraction occur at. So through this formula, you're able to calculate what the approximate halving time would be given a certain death fraction. So go ahead and fill in those values, the remaining values on the table, and then continue on to the next questions asking what happens to the halving and quartering times as the death fraction goes from 0.1 to 0.5, and state a rule that we might use to find the halving time if we're given 1 over the death fraction. Again, I did just give you a summary of what that rule would be. You can go ahead and write out your own rule that you would use to calculate in the future if you were ever looking for the halving time, given 1 over the death fraction and that value of 0.693. Moving back to the graph and the table, we do want to be sure that we lock this information so that way it is not lost in any future runs. So we're going to preserve the graph data and also preserve the table data. I'm going to go ahead and minimize those two the table and the graph. I'm going to put them back into my sector so that way I know which graph and table which question they're referring to. And we can go ahead and lock the next sector. For those who are curious about the number 0.693, if you go to the bottom of page 8 on the lab, there's a description of mathematically how we come to that number and why it is significant in regards to the halving time. You can go ahead and read through that. As explained at the top of page 7, there is another way to calculate the number of deaths per time unit in a population. This new method uses the reciprocal of the death fraction. The reciprocal is generally referred to as the dwell time and must be given an appropriate name depending upon the problem situation. Dwell time represents the average amount of time that items remain in the stock. For population models, the dwell time is usually called the lifespan. The death fraction of 0.1 per year is the same as an average lifespan of 10 years. Death fraction is the reciprocal of the lifespan. To calculate the number of deaths for the deer population in figure 2, we would take the number of deer in the stock and multiply it by the death fraction and get 20 deaths for the first year. To calculate the number of deaths in the deer population in figure 3, we would take the number of deer in the stock and divide it by the deer lifespan to get 20 deaths for the first year. Both methods produce the same result. The correct method to use depends on whether you want to identify the death fraction or identify the lifespan for the model you create. Just a moment, my battery is dying, so let me plug that in. So the next part in the lab is asking us to create the model shown in figure 2. It is the same as the previous model we've been using, so you can go ahead and copy that previous model we had been using and repaste it below. We do need to rename the death fraction to lifespan. And we'll also have to change our formula from deer population multiplied by the lifespan to divided by the lifespan. This is because the lifespan is a reciprocal of the death fraction. So if the death fraction were 1 over lifespan and you're multiplying that sum, you now have to divide the lifespan as it comes into the numerator. So I'm going to change that to division. Be sure to read through the entire lab as it gives you some essential information for what exactly we're looking at, be it exponential decay and the halving time or the half-life. I'm not going to read it here. I'm going to leave that up to you to go ahead and read through the remainder of the lab. But moving on to number 11, it says carbon-14 is a radioactive element that occurs naturally and decays into nitrogen. Carbon-14's dwell time is 8,225 years. Assume that you start with 100 grams of carbon-14 and sketch a Stella model diagram for the decay of carbon-14. Be sure to label each icon and then indicate the correct value or formula to place in each icon. Do not forget the units. As mentioned in the paragraph on page 9, the half-life is found by multiplying 0.693 by the lifespan. So go ahead and find that calculation and put it in the box below. It's also asking what is the value of the decay fraction. You can see how to find the decay fraction again in the paragraph on page 8. I apologize, I mentioned page 9 for the halving time as well. You can, it's page 8 that has the paragraphs that describe how to find the halving time. So go ahead and put those values below and how you found those calculations. So for problem number 12, it's asking us, it says, J has a 55-gallon barrel with a drain point. The barrel takes about 7 minutes to drain halfway. Create a model diagram whose behavior will simulate the draining of the barrel. So the calculations for the draining fraction. So with this, it's telling us that we have a 55-gallon barrel. So that will be our stock. I'm going to go ahead and replace this graph this model with this information. I'm going to label this water in barrel. And the lifespan we can rename halving time. And I'm going to rename the flow amount of water lost per minute. So now we'll need to change the value of our halving time. In order to find the halving time, it's given in the question. So it says the barrel takes about 7 minutes to drain halfway. So we're able to see that 7 minutes will be our halving time. And question 12 is asking us to find the draining fraction. So if we look at the fact that the barrel takes about 7 minutes to drain halfway, that's basically giving us a lifespan of how long the barrel will remain, of how long it will take the barrel to drain halfway. So if we take, since we want to find the draining fraction, this is similar to the death fraction that we saw earlier in the population values. So going back to that, given that the lifespan is a reciprocal of the death fraction, we are able to find the draining fraction by finding the reciprocal of that given information of 7 minutes. So the reciprocal of 7 minutes would be 1 over 7. And if we have that value, we can multiply that. Given that value, we can multiply 1 over 7 times 0.693, which will result in giving us the draining fraction. So go ahead and do that calculation. If you had some trouble understanding that, it would be 1 over 7 multiplied by 0.693, which would give us a value of 0.099. So that is going to tell us what the value of the draining fraction will be. Go ahead and change the halving time to draining fraction. And that value we found was 0.099. We have 55 gallons of water in the barrel. Be sure to change your units from deer to gallons, so you're not calculating how many deer are draining out of your barrel, because that would be kind of odd. And also be sure to change your units of the draining fraction as well. And now, because we're working with the draining with a fraction rather than a given lifespan, which would be a whole number, we can change that water in barrel back to multiplication of the draining fraction. And now let's take a look at what happens if we set a graph and the table to see the effect. Ideally, all we really need is a table on this, but I'm going to make a graph anyway so you can see the effect. And before we run it, let's make sure that all of the other sectors are locked and our table information is preserved. It is. And the graphing information is also preserved. Excellent. So now we can go ahead and run the effects of a draining fraction on the water barrel. Oops. You can see even the pros make mistakes. You have to make sure that the graph is showing you the value of the water in the barrel, as well as the table showing you the value of the water in the barrel. And as one would imagine, it's a fairly steady flow that it comes out. It's not linear, it is exponential, but it's relatively steady, and eventually it will approach zero but never actually move. And I believe the lab is asking us to find the half time of how long it would take for that barrel to drain about halfway. So let's just double check. So you want to calculate the draining fraction that I explained a minute ago here, and then it's asking how long does it take until there are less than 10 gallons of water in the barrel. So if we go to our table, we can see by scrolling down, out of the way, by scrolling down, that at 17 minutes, there are 10 gallons left in the bottle. So it would be after 17 minutes is when we would find that value of less than 10 gallons of water in the barrel. So there's the answer for that question. And finally, to finish, we're going to draw a loop diagram of your barrel model and label the arrows with the appropriate plus and minus signs. So you can go ahead and do that. If you happen to have any questions in regard to how to do this, please email your TA or professor so that they may explain this to you further if you don't understand it. We have dealt with counteracting loops and loop diagrams in the past, so you should be able to draw these on your own. But again, if you happen to have any questions, please feel free to contact your TA or your professor. Also, be sure to check with your professor if you're required to complete the journal assignments listed on the bottom. I know that a number of professors were replacing this assignment with a different assignment, but be sure to note if you are required to do those journals or not, and get them done. I hope this video was helpful. My name is Isaiah Ramos, and I'm glad to be of assistance. I hope you have a great day, and enjoy SBC 201.